news is we got the screen on there a lot faster this time. That's good. All right. People in the waiting room. All right. Cool. I think I'm also going to get rid of this whole waiting room business. Did you guys do any Zoom meetings for your classes last spring or in the summer? No, first one? Okay. Well, I think it'll be a little bit, hopefully a little bit better than the Blackboard Collaborate stuff. No waiting room. Okay. All right. So can everybody that's not in the room hear me okay? Hopefully.
Yeah.
All right, excellent. And you guys are all in, okay, so I'm actually looking for Reyes. Are you here? There's one of the students that blogged into the other one. That's why I'm a bit worried, but. Well, there's 44 participants and then there's roughly 15 of you guys. I think that kind of got mostly everybody. So seems to me like we're on the right track here. I'll keep my phone on in case somebody goes crazy and can't
I
find
have
it.
a question, sir.
Yeah, go ahead.
So how do we do the attendance on the iClick?
Okay, so for the iClicker account, well, the first thing I'll say is that for this next, this week and next week, I'm not going to be very strict on the attendance because people are still getting things set up, including myself. I'm using a different computer today, so, but all you have to do is log into iClicker, and that automatically, what I do is I pull the attendance list from that, like whether you logged in and participated or not. So, but like I said, I don't think I'll be using it for today's lecture.
Okay, thank you.
Okay, sure. Yeah, and everybody that's online, if you have questions, go ahead and ask anytime. Just interrupt. Don't do any hand raising or any weird business like that, because actually I don't even think this can do that. But just ask. Don't put things in the chat. You guys can chat all you want with each other, but don't expect me to reply while I'm giving the lecture, because you know, if I had an extra brain, I could, but it's just hard. So what I'm going to do then is going to go ahead and share my screen with everybody that's not here. And as I said, we're not doing the clicker stuff today, but because this computer is not set up with it yet. So let me get my other stuff. So everybody that's here, I mean, so are there any questions from last time that maybe haven't gotten answered? I know I've sent messages about the homework and the Pearson stuff. That's still kind of in the holding pattern. I'm waiting for them to fix a few of the links for the course. And once that's set up, I'll share it with everybody and I'll assign the first homework. The first homework, hopefully I get all this resolved in the next day or two. And if so, I'll assign the homework sometime this week and it'll be due in approximately a week, all right? So just be on the lookout for a message from me letting you know that it's ready for you to register.
I have a question about the book.
Yep.
You said last class that to hold off on buying the book until you get everything, I guess, integrated with Blackboard.
Right.
Is that still the case as of today?
Yeah, that's still the case. Like if you went ahead and got the thing that I asked you to buy, you probably can, but in a way it's a bit pointless because well, I mean, you'll have access to the electronic text, but I mean, there still won't be a homework out. The only difference is if you buy it yourself and you don't register through Blackboard, it might mean that you have to always access the homework directly through the Pearson side. And there could be issues with like synchronizing other things. So that's kind of why I'm asking for you to hold off. What I will do is I did finally get access to the slide deck for this class that uses that book. And I'll put that on Blackboard so you at least have all the slides that are more relevant. But yeah, like I said, just hold off if you don't mind.
I also have another question.
Yep.
When will the lab be? And is it going to be in person or online?
Okay. So anything that has to do with labs, and I think people have asked that question already. My short answer is I have nothing to do with the labs. And I think you should have gotten a message from Carla Carmona. She's the one in charge of the labs. And I believe they said they start September, what day, guys? Yeah, so September 7th is when labs start. And are they gonna be all virtual? Okay, so it seems like that message that you should have received says that it's going to be completely virtual and there will be 2 face-to-face meetings throughout the semester.
Okay, thank you.
All right, but like I said, if you didn't read that message in detail, go back and look for it and find it. I think there's a lot of information there, and maybe it's just easy to overlook it. All right.
I have a question. I'm sorry. I didn't hear you well because my internet cut off. But so we don't buy the online book yet, right? The online homework stuff.
Yeah, I would say hold off until I tell you that it's ready.
Okay. Thank you so much.
Sure. All right. Other questions? Anybody here? Questions? Okay. I know I asked everybody last time, but why did you guys decide to do hybrid versus online? Is there a real?
Trying to understand you through the computer is kind of annoying.
I had no other choice.
Okay. Okay. Others?
I just did.
I physically go somewhere. I feel more like driven.
Yeah, right. I see that. Okay. Somebody online was going to say something?
I said I joined it because I just feel like I'll get a better understanding of physics if I take it online rather than
Okay.
taking it like in person rather than taking it online, if that makes sense.
Okay. Yeah, so I mean, I think there's different reasons for everybody, and we got a little taste of it, right, last spring for people that were enrolled in spring classes where we suddenly flipped to like completely online. And depending on your teacher, right, it may have been a pleasant experience, it may have been a horrible experience. I certainly sympathize with the fact of needing to have a like structure in your life, right, in your daily activities, right? Because I have a son in college and he wakes up every morning and he decided to have structure because he's completely online, but he still wakes up at 7 in and showers and gets ready and dresses up and gets to work. And he doesn't even have Zoom meetings, actually. They're just all assignments for him. But I mean, it's difficult if not everybody has the same sort of organizational skills, and sometimes you kind of need that little push to shove you out of bed and show up and, you know, put on a bright, happy face. I also understand that online could be beneficial because you get to go at your own pace. If you want to go back and review something, you could watch the same lecture a few times if you have the time and interest. Yeah. Okay. Sure. Oh, yeah. And I encourage you to get even closer if somebody's willing to trade. You know, that's yeah. But it's you guys can work it out. But I completely understand because my wife is hard of hearing, and yeah, they have the clear ones, and I'll try to look for those. They look a little freaky, but they might do the job. But the other thing is, because I am recording all these, currently Zoom isn't really good at doing the automatic captions. But one of my plans because I'm teaching this class twice, the other one's completely online. My plan is to actually take all these videos and not only have them available through like the Blackboard Zoom kind of link, but I'm also going to upload them onto a YouTube channel because YouTube's pretty good at doing the auto captions and they actually work all right. And the other advantage of having them on things like YouTube is you can just play it at a faster speed if you get bored of me talking. You know, I might sound like a chipmunk, but the nice thing is all the text is there, so you could just read like, oh, makes sense, and you could stop it and then look at the things that are more interesting. So yeah, I'll try to be conscious about that. And you can feel free to call me out because I have a tendency, like today I'll mainly be using this thing. But in future lectures, I'm gonna be setting it up so that I can actually video record like the board as I'm talking. The only disadvantage of that, and I'll have like a microphone and all that so it doesn't sound like crap when I'm away from the computer. But I guess my warning to you that, and I give you permission to call me out on it, is sometimes I do this thing where I'm just kind of talking to myself and I might not talk as loud. So be like, hey, get out of the way. Let me see what's going on. Let me hear you better. That's fine. But you know, we're all human, right? So, okay, other questions? Hopefully, you know, you have a great semester and things, you know, progress the way they should. For everybody that's here live right now, today's lecture might be similar in the sense that the screen I'm sharing with everybody online is all you're gonna see as well. Like I said, maybe later we can use more space and it'll feel a little more normal. But so anyway, I guess that's all I have to say about that so far. And I'll go ahead and we'll continue where we left off, more or less. I know last time we started talking about motion diagrams and how we represent them and what kind of math we do with them. And we start talking about things like displacement. Let me just orient myself here. Okay, so let me see here. Last time we take a look at our cows and intersections. And I think it was somewhere around here that we stopped, right after this. So in this case, just as a bit of a recap, there's a couple of concepts that we've covered so far. One of them is what is the difference between distance and what is the difference between displacement? Does anybody have an answer to that?
So displacement is like the change in position of the object.
Okay.
And distance would be the amount, the way it travels.
Yeah, so let's go back to, so change in position. And this is the part that we talked about last time. So it could be something like delta x. So the delta means change in. And yeah, because we're looking at a difference between two positions, we're gonna take a final position minus initial position. Okay, initial. And you're right, that distance, that one's a little bit harder to quantify, to say, because you want to use the same word in the definition, right? So it's total path taken is really what it is. And in this case, distance is also always a positive value. Now for displacement, it is a change in position. And in this case, it can have a sign. It could be positive or negative. And that sign indicates direction. Okay. And that's kind of where we left off last time, where we said, okay, well, we've got this intersection and, you know, we're starting off, in this case, they start off at position of 50. And so that would be our x initial. And they end up at the intersection. And hopefully you guys all have the copy of these slides and you're following through, because I know it's small on the screen. And so we end up at x equals 0 as our x final. And so to get the delta x, you're going to get x final minus x initial. That's going to be 0 minus the initial position was 50. So that's going to give you minus 50 feet for our displacement. So in this case, that negative sign tells you that we're moving left in this cartoon, right? Because that intersection has it so that that's positive x, and then to the left is negative x direction, all right? So those are the main things. Distance, total path you take, displacement is the difference between the final and the initial position. A really nice example is, let's say you go to a track, maybe you run track at some point in your life, and you go and you do a mile, right? It's like, what is it, 4 times around the track, right? You're tired and you're beat. You're like, oh, that was a lot of work. It's horrible. And then somebody gives you a stupid physics question like, well, what was your displacement? Well, guess what? It was 0, right? You ended up in the same spot. And that's a really good example that even though your total distance was 1 mile, your displacement is exactly 0, right? Right now, well, when you guys get back on your cars to drive back home, your displacement is 0, right? From when you got off the car to when you get back on the car. But the distance was the path you took to get here. So, and those definitions are important, and those are conceptual things that you'll be tested and quizzed on throughout the lecture. So, just like we can have, one of the things that we saw with displacement, there's a reference point, right? Somebody said, well, 0 is in this place. In that case, it was the intersection. We could have chosen 0 to be the starting point, and then you would have gone to -50. So just to, before I talk about that slide, you could say also could do, so this is an alternate way of doing it. You could have said, well, what if I start here and I walk that way? In this case, you start at 0 and you end up at -50. These are kind of like an equivalent problem. We just put this reference point out there. So that's one thing that's kind of nice about these quantities is the reference point. You just have to define it and then give your answer relative to that reference point. And so you could do the same thing with time. So for example, in this case that we have on the slide here, you've got your number line and somebody decided to make 0 out here already. But when you look at the motion diagram, well, in this case, this motion diagram, and actually I'm getting ahead of myself a little bit, but let's just talk about this. Because we already talked about distance, displacement, but now we also are going to have to keep track of the time intervals. So in a motion diagram, if you start off at 0 seconds, you're at x equal 0 feet. So notice one thing that's also important. You always want to make sure you label your axis and that you put the units on there. Units are going to be important in this course. So you might have a little number line that kind of goes across like that. And so in this case, this might be your initial position, this might be your final position, and you have your final time out here of 6 seconds. Well, at a time interval, anytime you see time interval, we're also going to call that delta t, so that's a change in time. So the idea here is anytime you define an interval, it has a start point and it has an end point. So it'll be the final time minus the initial time. And it's a quantity that's always positive. Now, we'll get into a little bit of the reference point stuff in a little bit here. But let's go ahead and do this example, just to make sure that we're applying the concepts correctly. So in this example, it says, Carol is enjoying a bicycle ride on a country road that runs east-west past a water tower. Define a coordinate system so that increasing x means moving east. At noon, Carol is 3 miles east of the water tower. A half hour later, she is 2 miles west of the water tower. What is her displacement during that half hour? And there's a little comment, they're like, oh, what's the point of doing all this craziness? You could just look, right? And if you look at the picture, you can see, well, you started at 3 and you ended up at 2, and you can kind of count them and you're like, oh, well, that's 5 of them, right? You can tell it's 5 miles. And they went to the left, so it's a -5, and then you'd be done. But the whole point of this is to get you in the habit of knowing how to write down these word problems and turning them into a problem you can solve. So we first start off with our axis here. And so they talk about this water tower. And so maybe the water tower is going to be our nice little reference point that we're going to use. So we'll make our water tower be our little 0 position. And so they start telling us more information like, well, they talk about east and west. So the moment we put our reference point on our number line, well, we have to make that connection with reality, right? We need to know, okay, positive x in units of miles, that's gonna be also the direction of east, okay? And just in case you forgot your cardinal directions, up is north. Usually this is how you see it. Up is north, down is south, west, east, like that, okay? I know people in college that don't know this yet, so I'm doing it for you guys. But okay, let's continue. It says, so at noon, she is 3 miles east of the water tower. So we're gonna go to the right and we say, okay, here we are at noon. So the position X initial is 3 miles. Time initial, we can say it's noon. And then it says a half hour later, she's gonna be 2 miles west of the water tower. So now we're gonna go on the other side of the water tower. That's 2 miles. We'll put a negative on there because it's still left of 0. And so that's gonna be our X final. And our T final, because it's half an hour, right, will be 12:30. So right away, we know there's a delta T of 30 minutes, okay? And it turns out in this case, I don't think it's a necessary thing to know. All we need to know is the displacement. And so for the displacement, we're gonna get to use our equation. That's delta X equal to X final minus X initial. So the final position was -2 minus the initial position was 3. So -2 minus 3 is gonna give us -5, and the units are miles, okay? And so one of the things that we'll start doing later in the course is using these arrows that are called vectors. And we'll talk about those more later. But basically, this is a displacement. This is a way of representing a displacement. It was -5 units to the left. Yeah. All right. And so here's the problem worked out. And so one thing to watch out for is just make sure that if there's a negative for the position that you put it down. Make sure that you're doing minus the initial. So one place that people can get caught up is, well, right now we got lucky in that negative is a minus of a positive number. So, but if you had, let's say a -4, then it'd be minus -4. So those two negatives turn to a positive, right? So this is your standard algebra you gotta be sharp with, all right? All right, so 5 miles. All right. So let's do, so this is where I would usually give you the clicker question. So it says here, Maria is at a position of 23 meters. She then undergoes a displacement of -50. What is her final position? So once again, we write down our displacement equation, X final minus X initial. I always recommend that you just draw it anyways if you're more of a visual person. Because that way you could say, okay, well, X initial was 23, X final. Well, actually it says her displacement was -50. So we know it's gonna be -50 that way. But in this problem, really what they're doing is they're asking you to find X final, right? So we know X initial was given to us, it's 23. We know the displacement, delta X, was given to us, it's -50. So all you gotta do is you have to take this and solve for X final. So you're gonna get X final is equal to displacement plus X initial, right? And so, and if there's any questions, stop and ask me. But in this case, delta X will be -50. Plus the initial is 23. So -50 plus 23 is going to give you -27 meters for the final position, all right? And so that's how we get that answer. So here's another question that's going to ask us to think about both distance and displacement. So in this case, it says an ant zigzags back and forth on a picnic table as shown. They want us to tell the final distance traveled and the displacement. So first of all, looking at this, before we even, well, let's actually draw the picture real quick. Because it's nice to kind of get a little visual representation. Basically, we have this motion that looks like that, right? Actually, not exactly like that. That's the part that I always get hung up on, is like, oh, did I draw it exactly right? But you'll find that we don't even need to know exactly where those little points are on the path, because all we know is when we do this problem, the x initial is right here, x final, that right there, that's going to be x final. So we know that in terms of the magnitude, the distance is going to be a greater in magnitude. So the magnitude, or the size of it, it's going to be bigger than the displacement, right? Do you guys agree with that? Because for the distance, we're talking about the entire zigzag path. But for the displacement, we're just looking at the difference between the initial and the final, right? So our displacement delta x will just be that distance. So we already know from looking at those numbers, those options, well, definitely we need to have big distance and small displacement. So you go through the list, and the only ones that satisfy that are C and E, right? So C or E, which of these? Because in this case, that satisfies distance, bigger magnitude, and displacement. Now, the next part is to say, okay, well, we know the displacement is negative, right? We're starting on the right, and we're moving to the left on that number line. So we need to have a negative displacement. So when you look at C and E, well, E is the only one that does that. So E has both big distance and small delta x, and it has a negative delta x, which is what we're looking for. And so for this one, answer is E, okay? So you don't even have to check and see like, oh, is that a 15 on the x-axis, or is that a 35 or a 40? Who the hell knows, right? It's drawn weird. But I think that's the point on purpose, so that you can think about, just by looking at the picture and knowing the difference, you can figure it out. Any questions? All right, so the next thing is we're gonna go to studying velocity, which is kind of the next level up in terms of concepts. And so we've already talked a little bit about things like distance, and speed. I think we talked about speed a little bit at the beginning of last lecture. But there's some definitions we gotta make here. So anytime you have motion at a constant speed, and it's in a straight line, we're gonna call that uniform motion. All right, so uniform motion, this is one definition here. Now, when we talk about things like speed, this thing here, the way we calculate speed is going to be distance. I'll put the word total just to help you realize it's not displacement. It's the total distance in a time interval. That distance in a certain time interval is going to be divided by the time interval. So in this case, the units are going to be units of distance over time, right? And so examples are, your speedometer. One example could be miles per hour. Anytime you see anytime you hear anybody say per, it means you're dividing by something. So miles per hour, we also just use MPH for that. That's what you see sometimes on your car when you're driving. And so that's all it is. It's just the total distance over time. Speed has no direction, okay? And that's one distinguishing feature between speed and velocity. And we'll talk about velocity shortly. All right. So in this case, we've got a problem where it says Jane walks to the right at a constant rate, moving 3 meters in 3 seconds. At t equals 0, she passes the x equal 1 mark. It says here, draw her motion diagram from t equals -1 to 4 seconds. So you're like, okay, well, so there's a few key things that they've given us here. One of them is that she's moving at a constant rate. So, not what I wanted to do. So we got let's call this the Jane problem. I've got a problem with Jane. We need to talk. So in this case, constant rate is important for us to know. So we know her speed is not changing. It's constant speed the whole time. So constant speed really is what they're saying. And we can check that because they tell us that she's moving 3 meters in 3 seconds. Well, if you do 3 divided by 3, that's going to tell you that she's moving at 1 meter per second. So every second she travels a meter. You guys have an idea how fast you guys walk? You guys ever thought about that? It's about
all the time.
Yeah, you can think of when you're walking, usually a step is about 3 feet, and 3 feet is pretty close to a meter. So if you're walking and you can count like 1, 2, 3, that means you're probably moving that fast. Most people walk a little faster. But one thing you could do one of these days, if you're just bored and maybe part of an extra credit thing, is you can just start your timer and start counting your steps. And then stop the timer and then compare to how many steps you took, and that can help you calculate your actual speed. Right? It's kind of, might help you realize, how many minutes it takes. I mean, you know how many minutes it usually takes you to walk around campus, but if you want to do it nerd style, you do it in meters per second, and it's kind of cool. But anyway, let's do this problem. So we know she's moving 1 meter per second. It says at t equals 0, she passes the x equal 1 mark. So where's the x equal 1? Well, we don't know yet, but now we do because there's a 0 here. And so we could put 1 meter per second. Oh, nope, sorry, not that. So this is the 1 meter mark. And this happens at t equals 0. So t equals 0. And then it says, draw her motion diagram from -1 to 4. Well, okay, well, so far we've only got 1 point, but we know that she's moving at 1 meter per second. And the other key information is she's moving to the right, right? It says it in the problem. So to the right means she's going that way. And we know she's gonna cover 1 meter every second. So if we fast forward to t equal 1 second, well, she's gonna be at a distance of 2 meters. You go to t equal 2 seconds, she goes to the next spot at 3 meters. And you go 1 more second, t equal 3 seconds, she'll be here at 4 meters. So that goes right there. And then 1 more second takes us here, so that at t equals 4 seconds, she'll be at 5 meters. So that does it from 0 to 4 seconds. They're asking for -1. So all we need to remember is because she's going at a constant speed, then obviously if you subtract the second, t equal -1, she must have been at x equals 0 at that point. And so that's essentially your motion diagram for that problem. And so we took advantage, we took pretty much all the information given in the problem to write this down. Questions? Yeah. Did I write down a 3.5? Oh, it's a 3 seconds, maybe? Yeah, sorry, yes, right here. This is supposed to be an S for seconds. But technology, and I'm sloppy too. Actually, one thing that's kind of cool, I don't know if I should do it right now though. This lasso effect sometimes does a good job at like getting the text out. But I'm afraid that it'll not do it quite right. Yeah. It starts writing weird stuff. So I won't do that. Question, yeah?
So it was constant speed is equal to 3 meters per 3 seconds? Or was it 35?
Well, I meant to say 3. So she moves 3 meters in 3 seconds. So that is the same thing as saying 1 meter per second. That makes sense?
Okay, thank you.
Sure.
Yeah, makes sense.
Cool. All right. So as I mentioned before, speed is only telling you how fast the object's moving. It's telling you this distance is in this much time. But the difference with velocity is going to tell you the speed and the direction. So if we go back one slide here, let's make a new little line here for velocity. Let me get my right tool here first. So for velocity, as the slide says, gives you both speed and direction. And direction is really the critical thing here. So it's not good enough to say 50 miles an hour. We want to know where. 50 miles an hour south, 50 miles an hour to school, 50 miles an hour, you know, off the bridge they're building at the Spaghetti Bowl because you didn't pay attention to the signs telling you everything's closed, etc. It's a direction. It tells you where you're going at that speed. And so when we write down the equation for that, it's a bit different also, where we can say velocity, now the calculation is not going to be total distance, but we're going to deal with displacement. So velocity also only cares about the difference in position over time. So it's displacement over time interval. So that's going to be delta x over delta t. All right. And so you'll notice when you look at the number lines in the example on the slide, you're going to use an arrow to indicate what way you're going. So if you're going from 0 to 20, that's a positive direction. That arrow is going to point to the right. If you're going in the negative direction, for example, bike number 2 is going from 120 to 100. That's a negative displacement. So it's going to be a negative velocity, telling you that it's going to the left. So let's go ahead and do this, this example here. So in this example, it says it's about a seabird. It says albatrosses are seabirds that spend most of their lives flying over the ocean looking for food. With a stiff tailwind, an albatross can fly at high speeds. It says satellite data on one of these albatrosses showed that it was at 60 miles east of its roost at 3 o'clock. And then at 3:15, it was 80 miles east of its roost. And so they want to know what is the velocity. So for this problem, and these are all supposed to be horizontal lines, but hopefully you realize that. The reference point is going to be the roost. So reference point is where we make it x equals 0. This is the roost. And so then it says that in the first observation of this bird at 3 p.m., let me put that on the top instead. We can call this our T initial, it's 3 p.m. It was located at 60 miles east. So this positive x direction is also going to be the direction of east. And I always encourage you to just write yourself a little northeast, southwest thing just to, in case, it's nice to just see it in front of you in case so you don't make errors. And then it says at 3:15, it was located at 80 miles east. So the final time here might be 3:15. And so we want to know, what is the velocity? Well, and what it says there is also a tailwind, right? So that means if you've got your bird here, I don't know what an albatross head looks like, but a tailwind basically means it's a wind that's kind of hitting the tail of it. And so you already have a little bit of a hint that, well, it might be going faster than it usually would when there's no wind, right? You guys ever see birds when it's really windy? Like if they're going with the wind, they haul ass, right? And if they're going the opposite way, like they kind of stay still, right? Or they even go backwards, right? Because they just can't fight the wind. So we kind of know he's going to be going fast. So let's see this velocity calculation. So we said velocity is going to be displacement delta x over delta time. So we can calculate delta x separately here. We have delta x is, we know it's final minus initial. The final position that we saw it at was at 80 miles. So in the problem, when we set it up, 60 miles was the first position, 80 miles is the final position. So we're gonna have 80 miles minus 60 miles gives you 20 miles, okay? And it's a positive value. So we know it's moving to the right or in the east direction. And so we get to put in our equation for velocity in the top, we'll have our 20 miles listed there. Now let's look at delta x. So delta t. So the final time was 3:15. The initial time was 3. So the total time change was how many minutes? I'm just checking, make sure you're paying attention. It's 15 minutes, all right. So we could put 20 miles divided by 15 minutes, but usually we don't talk in miles per minute, right? We like things we're used to. Miles per hour is more common. So how many hours is 15 minutes? Did I say miles? How many, did I say, I meant hours. How many hours is 15 minutes? Yeah, so it's a
0.25.
Yeah, so you can have it be 1/4 of an hour, or you can write down 0.25 hours. It's the same thing. But you end up putting 20 miles divided by, let's choose a 1/4 hour here. Makes the math a little easier. So 20 divided by 1/4 is gonna be 80. The units are miles per hour. So this seabird is going at 80 miles an hour, and it's a positive value, so it's moving east. And in any problem you do, when they ask you for velocity, you want to make sure you always give both the magnitude, in this case 80 miles an hour, and the direction, which is either positive or east. You know, you can use either one as acceptable. All right, questions?
When it comes to the time, it always has to be an hour instead of a minute.
It depends on the problem. In this case, it's just a little bit more intuitive, right? Because we're not used to thinking miles per minute. Usually, so one thing that you'll notice in general with any of these problems is we don't like to mix really big units with small ones. Because if it was miles per minute, like it's hard to think about that, I guess, is all. But the answer is no, not necessarily. Sometimes your answer will be in seconds, sometimes it'll be in minutes. You have to go with whatever they're asking you for. In this case, it was just my preference. We could have just done 20 divided by 15 and said that number, you know, so 1.25, I guess, would be miles per minute. But like I said, it's just not a conventional way of describing it. And so you'll see that that's exactly what they did in this problem. They did 20 miles divided by a 1/4 hour, which is 80. But you could have, in principle, so this answer here is correct. I mean, you could have also done, like I said, 20 miles per 15 minutes. And so in this case, 20 divided by 15 is what? 4/3, 1 and, no, 4/3, 5/4, is it 1.25? Is it? Come on. Is it 1.3333?
1.3 for here.
Anyway, round it up to. So basically, in this case, it's 1.333 miles per minute. But in the interest of not making this too cluttered, let's move on. All right. So let's see what's next here. I encourage you guys to work on these example problems to make sure you can do it on your own. They're very similar to the one we just did. So I did want to spend some time talking about things like significant figures, scientific notation, units, because this slide kind of has it all, right? We just did, well, we didn't do significant figures too much, but we will. I mean, we wrote down this decimal, that 1.33333. And the question is, well, do you have to put all the threes all the way to infinity? The answer is no, right? There's a certain number of decimals you put that makes sense, that is expected actually. And that's what we'll talk about next is how do you report how many decimals you put? And this is not just something that applies to physics class. Any kind of science class is always gonna ask you to put the right number of decimal points. we just did unit conversions, right? We went from minutes to hours. So we're gonna spend a little bit of time on that just to make sure we're on the same page. And a lot of times this idea of how many decimal places you put has to do with this concept of precision, where the number of points tells you, well, how well do you know that number? I mean, if you get a standard ruler, it's 12 inches, right? In the first inch mark, depending on the ruler, you may have a certain number of separations. So for example, if this is your 0, maybe this is 1 inch, etc. You know, they usually have a little split right here at the half-inch mark. Most of them will have the quarter. Sometimes you'll have another little separation here. These are like 1/8 inch marks. And so in this case, if somebody tells you like, well, I'm at position, 1 inch. Well, there's an error associated with that, right? Because of the closest you get to a tick mark, so, what if you're right here in between these 2 points? Well, you don't necessarily know what that number is. So you have to introduce some error. So you say, well, yeah, it's 1 inch, but it's plus or minus whatever that deviation is. And in this case, if this deviation is like 1/8 of an inch, then you might say, yeah, maybe plus or minus 1/8. And that's officially the way that you kind of report that. And so in this case, 1/8 of an inch is, you can turn it to decimal, and that kind of gives you a sense. But that's the whole idea and why we stress it so much. Because you can take a number that's not very precise, like, you could take the number 10, whatever that 10 is. But if you divide it by something like pi, well, you guys know that pi is this crazy number that it's infinite, right? It's 3.14159, etc. Well, you're going to get a number with a huge decimal, and we got to learn how to chop it and put the right decimals. So that's kind of what this is about. And I'm going to blow up this slide, but it should be slide 53 in your deck of slides. And so there's some rules behind how you do this. And you're going to do it differently when you're doing multiplication, division, taking roots. That's going to be one way. If you're doing adding and subtracting, there's a different way of writing them down. When you multiply and divide, it says here, you're going to take the number of significant figures of the least precisely known number used in the calculation. So when you look at that example, it says 3.73 times 5.7. Well, in that case, you have the 5.7 has the least number of significant figures, right? One of them has 3 numbers, the other one has 2 numbers. So the rule is your answer is only gonna have 2 significant figures because that's the one that's least well known. So that's a 5.7. So if you type it in your calculator, you'll see there's decimals after that 21, but when you actually write it down, you should only put equals 21 because of the decimals. When you add and subtract, instead of the number of significant figures, which is how many digits you have, you're gonna look at the number of decimal places. And once again, you're gonna take the number with the smallest number of decimal places in the calculation. So in that case, 8.54 has 2 decimal places, 106.6 has 1 decimal place. And so guess what? Your answer is only gonna have 1 decimal place because that's the one with the least number. And I mean, obviously they're only showing 2 numbers here, but you could have 4 or 5 numbers, and you gotta make that choice of which is the one with the lowest number. So just to, well, actually, before I make this small again, there's a few other kind of exceptions. I mentioned already, if you have numbers like pi, well, they don't have any uncertainty. So in that case, if your calculator lets you punch in pi, then you use that full number. Another part is if you're doing a problem that has multiple steps, let's say you have to multiply a few numbers and then subtract them from something and then take that and multiply it times something else. In those cases, if you're using your calculator, I recommend you just keep a lot more decimals than you need in those in-between steps. And it's only at the very end when you have your final answer that you check and see all the numbers you use to like trim down the number of decimals on it. So let's go ahead and kind of give you a little bit of a what do you call it, Cliff Notes version of that slide. So basically, what it says here is, so for significant figures, so significant figures, and I'll call these sig figs just for short. There's two methods, like I said. When you multiply and divide, the idea here is you keep smallest number of significant figures in answer. So in this case, if we look at that example of 3.73 times 5.7, well, guess what? This one has three significant figures. This one has 2 sig figs. And so your answer is only going to have 2 digits. So when you multiply them, you're just going to keep that 21. Now, where am I? So in that case, yeah, okay, so the answer is just, so, oh yeah, what I was gonna say, so let's say your answer was 21.6 something something. Well, you're expected to round to the nearest value, right? So hopefully that's obvious. The other one is when you do adding and subtracting. Let's just do here, add / subtract. As I mentioned, you're going to keep smallest number of decimals. So let me put the example over here this way. So we have 18.54 plus 106.6. That's going to give us 125.1. So we only keep that first decimal. Obviously, if you were to run this through, you'd notice it should be a 1.4 there. But because in this case, this number has 2 decimal points, the next one has 1 decimal point, then your answer here has to be 1 decimal point. Decimal in answer. All right, so, and the other reason I'm going over this is because when you do the homework, you might be asked to provide your answer to 2 significant figures or provide your answer to 3 significant figures. So you gotta know how to do that. All right, so here's another quick check that if we were using Reef, I'd ask it with Reef. It says to rank in order from most to least the number of significant figures in the following numbers. So if B has more than C, then hopefully you understand the way we're expected to put greater than or less than or equal signs. So in this problem, let's look at the numbers real quick. So we've got A is 8,200. B is 0.0052. C is 0.430. And D is equal to 4.321 times 10 to the minus 10. So let's start off with the first one. How many significant figures would you say that has? Yeah, so in this case, 2 significant figures. Now that one could be ambiguous also. And the reason is that it could be that you don't know, there's just not enough information about that number. It could be that maybe you took a really precise ruler and you know it's exactly 8,200. Not a 8,201, not 7,999, but it's 8,200. It could also be the case that your ruler that you're using is only accurate to the nearest 100. It could be that it's, it could be that it's like 8160 or 8240 or something like that. And so because of that, it's it's a bit questionable, right? Sometimes those zeros actually, sometimes they put them there on purpose. In this case, it's hard to tell. What about the next one? Yeah, so the next one's also 2. In this case, the zeros are just placeholders. Because you can also take this number and express it as like 5.2 times 10 to some power, right? What about the next one?
I'm sorry. I had a question. Were the polls supposed to come up on my reef? Because I don't have anything.
Yeah, we're not doing reef today,
Okay, all right.
right? Don't worry about it for now. Yeah, so, and then for C, it's 3 significant figures. And so the question is, well, why? Well, so obviously these 2 are significant. Which is the third one? Yeah, so it's going to be this 0 is the correct one. So why is that one significant? Yeah, so I mean, I guess you could have, I mean, the number is the same when it's 0.43, but yeah, that 0 is telling you something about the measurement. It's telling you, actually, we know for sure it's not 431 or 429. It's exactly 30. So that 0 is put there on purpose to let you know that there's precision there. So that's why it's 3. What about the last one? Yeah, so that one's 4. So in that case, this one is just to scale the number. Doesn't really, it's an exact number that you're multiplying the first numbers by. So in this case, doesn't count in terms of determining significant figures, and it's only this right here. So it's 4 significance figures. And so when we look at the answers, you'll see that you guys are kind of on the ball here. It's so obviously D had 4, so that's the one with the most, followed by C, and then B and A both have 2 significant figures, right? Okay. So we just showed an example of scientific notation, this times 10 to the power of something. And so we're gonna use scientific notation to represent really big numbers and really small numbers. But first, I need to connect my laptop, otherwise we'll have no power. And so give me a second. Is that one that's taped up? I can put one on my side. I'm just, hopefully I don't trip. Got one back here. Maybe there's one in here too. Hold on. I feel like somebody doesn't like instructors. Oh, here it is. I guess we're expected to use our computers, but sometimes those computers are, I don't know, not the best. All right. So yeah, so let's talk a little bit about scientific notation, hopefully not too much time. But the idea there is, if you want to convert really big numbers to something that fits on your paper. So in this case, the first example shows the number, I guess that's 6,370,000 meters. Well, if you don't want to write so many zeros, in this case, it's not so bad. But if you think about things like the mass of the sun, does anybody have any idea the mass of the sun in kilograms? It's a huge number. It's something like 10 to the 30 kilograms. Like I think
At least 12.
Is it 12? What was that? I heard somebody say something. Anyway, but yeah, the idea is you can't write down a number with like a bunch of zeros, right? I mean, you can, but it'll take a long time. And there's even other quantities in the universe that are so big that you could spend your lifetime trying to write the number down and you'll never get there. Same thing with really small numbers. If we look at, if I asked you what's the distance between the atoms in your body, does anybody have an idea of what size that number is on average? So they're tiny numbers. You may have heard of quantities like nanometers. You guys heard of a nanometer? What is a nanometer? Uh-huh. So nano is related to the word 9. So in this case, it's 10 to the minus 9. It's a billionth of a meter. So 1 nanometer is equal to 10 to the minus 9 meters. Or you could say 1 billionth of a meter. But imagine doing like sciencey stuff that way, right? You're like, oh yeah, well that's 1 over, you know, it could be a 1/2 billionth of a meter. It could be something like this. And so in case you don't remember, you know, so that's a lot of zeros, you know? And then imagine you have to take that and add it to another one, and you're gonna have pages and pages of stuff. And so that's why we take that 10 to the minus 9 as a shortcut to writing small numbers. So since we're on the topic of nines, you know, so nano is a billionth, 10 to the minus 9. What is the prefix for a billion? Anybody know? So a billion, that's a giga. So you guys have, where have you heard the word giga before? Yeah, so there's gigabytes and giga, what else? So 1 gigabyte, that's basically 1 billion or 10 to the 9 bytes. Another place you might have heard of it is like with cell phones. So they work on gigahertz ranges. That's a unit of frequency, how quickly the little fields oscillate back and forth. And so that's the same thing. It's 10 to the 9 hertz. And then in this case, and we'll get to that later in the semester, but hertz is it's a unit of frequency. It's telling you that there's 1 billion little oscillations happening every time you're talking on the phone. You can imagine these little waves just kind of trickling in and out of your phone. It's also the frequency of microwaves for your food that you heat up. So there's a reason why we do scientific notations, because sometimes we deal with kind of big numbers. And so let's go ahead and write down the rules that are on that slide real briefly. So in this case, so scientific notation. So let's say we're going to go with a number like what they have there, 637,000 meters. Well, in this case, if you want to go from, basically we're going to go from what looks like a, well, I don't want to say big. Let's call this, we go from lengthy to compact way of writing the same number. Well, in this case, what we're going to do is the number is going to look like 6.37. Okay, so how do we get that? Well, the idea is the goal is always to have only 1 digit to the left of the decimal. That's always the goal when you're doing scientific notation. And so what does it take to do that? Well, we're starting here. That's where our decimal is. And we're going to the left 1, 2, 3, 4, 5, 6 spaces. So 6 spaces. And because we're going to the left to make it what looks like a small number, that means that whatever we put here has to make it big. It has to kind of make up for it, right? So 637 is little compared to that 6 million number. So now up here, we got to put the number of spaces, which is 6. So it's 6.37 times 10 to the 6 meters, okay? So this is what we do for big numbers. Where's the cursor? I'll put big numbers. And if you want to deal with small numbers, this is what's coming up next. Well, we're going to do something similar. So if we use that number that they have there, it's 0.123 meters. So that's a tiny number. And so the idea is still to have 1 digit to the left. So we know it's going to be 7.5 times something. And so we're still going lengthy. You know, this is the lengthy number to compact. So we're gonna go from that period, we're gonna go 1, 2, 3, 4, 5, 6 decimals over. In this case, it's 6 to the right. And because once again, in this case, it's the other way around, right? So we had a tiny number and we kind of made it a big number with that 7.5. So now we got to put a number here that's going to make it small again. So we have to put a negative. This means it's going to make it little, a -6. So that's the scientific notation way of writing small numbers. So this would be 7.5 times 10 to the -6. Right? Any questions? Make sense? Hopefully. And you'll be expected to just do this naturally, right? I mean, throughout the semester. So just get in the habit of just converting things just for fun. Like, you know, in your spare time, you could be like, oh, how much do I weigh? And you could even Google it to check to make sure that you're doing it right. Anyway, so the other thing that I want to mention briefly is that the units that we use in this class, most of the time for units, most of the time, we will use the SI unit system. So this is it's a French word, but it's basically the International System of Units. That's what it means. That's what I don't want to butcher French because in case people actually speak French here. But the idea is to try to be, so the SI unit system is an attempt to make a universal system of units so that we always know what we're talking about. So whether you're communicating with people from another country that use different units, hopefully everybody can do SI. It's not always the case. But so some examples, and there's gonna be more of them. And every time I introduce new quantities in this class, I'll tell you the SI units are, you know, blank. I'll tell you what it is. So, some examples of things we've talked about sometimes are time and length. And so the unit's going to be the seconds is the SI unit for time. And meters is going to be the SI unit for length. And we're going to use different abbreviations for them. So seconds is going to be an S. And this goes back to the question earlier, like, oh, why does it say 35? Like, no, actually I meant to write 3S for seconds. So now you know. And meters, we're going to just use a lowercase m for meters. Later on, we're going to talk about quantities like mass, and the SI unit is the kilogram, and the abbreviation is going to be kg. And there's going to be many others, like I said. But one interesting thing about this that even to this day, it kind of kicks us in the ass is, I don't know if a long time ago, okay, first of all, do you guys know what the International Space Station is? Okay. What does that thing do? Where is it? Yeah, it's up there, yeah. Yeah, so it's what it sounds like. It's a space station. It's this international collaboration that includes, you know, it's like people from Russia, the US, China, other countries. And actually it's a worldwide effort, and you know, sometimes people go up there to just study, you know, what happens to bodies in microgravity, what happens, they do experiments to test, you know, all sorts of stuff. They even use it to observe the earth in different ways. But because it's an international collaboration, what happens sometimes is you might have one team building a module that they're going to go attach up there. Can you guys think of something recent that happened that was able to connect to the space station? Yeah, so SpaceX, right? First private company funded by the government, though, to actually connect something to this thing that's been floating in space since like the 70s, I guess. And they did it successfully, and it's like, oh, great, cool, we did it, good job. We are not paying attention because we're dealing with people dying and COVID and all this crap, but it's pretty monumental. It's on the same footing as like first man on the moon kind of stuff, you know. The other big thing is they're getting, you know, reusable rockets to drive down costs for space exploration. But my main point of what I'm talking about is they had to make sure that the stuff they built here on Earth, when they send it up there, it's gonna fit, okay? Well, there was this huge issue of about 20 years ago, maybe almost 30 years ago. I think it was sometime in the 80s, where one of the teams designed the part, and according to the instructions they were given, they build it, they launch it, they show up, they're like, all right, let's put it together, take out the bolts, whatever. And then they're like, oh shit, somebody used inches and somebody else was using centimeters. So it didn't fit. You spend millions of dollars on something and it doesn't fit when you get there. So that's a big deal, right? I mean, but these are things that happen often, right? You might be at some point having to inject somebody with some kind of medication. Well, you want to make sure you know the units, right? Are we talking about milliliters? Are we talking about milligrams? Or, you know, is it microliters? What kind of flow rates, you know, and all these things require that you pay attention to units. It's critical, right? One of my favorite things is when somebody's like, oh yeah, I'll be there in 10. Yeah, we know that usually means 10 minutes, right? But maybe that for some reason, maybe they actually meant to say later in the day, like 10 hours, and nobody talks like that. But that's another weird example where sometimes you need to know, like, what are you talking about? Tell me the units, you know? So it's important. And I usually don't mark off on homeworks where you don't put the units if it's like something you submit to me in person. But for people that repeatedly do it all the time, I'm gonna be like, hey, what the hell, man? Minus 10 points because units matter, you know? The other reason why units matter is it helps you figure out whether you did your problem correctly. And we'll go through some examples of that later. Because if you need to write down an answer that's in meters, but you write down your answer in seconds, well, that doesn't make sense. You know? So, and sometimes we'll talk about dimensional analysis a little bit later. But actually, we're kind of getting close to the end of class, but let's do this unit conversion thing real quick because, like I said, this is one of the things you'll be doing all semester also is you might be giving a problem that is not in SI units. Maybe they'll give you something in miles like they have here. And you might need to convert that to kilometers. And so there's a method of doing that, just like we did with the, you know, doing the conversion of time. The idea there is, that's not what I meant to do, but okay, let's see. Let me just open up a new one here. So the idea there is, let's say that you want to convert something like 60 miles, and the goal is to get to kilometers. Well, the first question is going to be, well, how many miles are there in a kilometer? So if you look it up, there's tables on your book and you can Google it. Turns out 1 mile is roughly 1.6 kilometers, or I think it's exactly 1609 kilometers. I think that's what the text here said. Let me actually get to that. So in that case, the way you actually calculate it is you'll take 60 miles. And always, whenever you're doing conversions, you can always imagine that number you're trying to convert. Think of it as a fraction. This is actually 60 over 1, right? You're like, yeah, sure, weirdo. But the reason for that is you always, when you multiply fractions, you know you multiply fractions, the numbers, you just multiply them across, the bottom one's across, and you get your fraction at the end. That's the same idea. And also, you're going to want the things in the bottom to cancel with things in the bottom. Things in the bottom cancel with things in the top. So you might have, in this case, since we want to get rid of miles, well, you'll put 1 mile in the bottom, 1.609 in the top. And that's going to take you so that miles cancel. And all you're going to do is going to do 60 times 1.609. And you find that the answer is 97 kilometers. We could do that same thing with the previous problem we did with time, right? Remember we had 15 minutes? Well, we know it's a quarter of an hour, just because if you ever were learned to tell time on one of these things, well, right away, you know that that also means 15 minutes right here, and 30 and 45 minutes. And so 15 minutes is basically a quarter of the pie, so it makes it easy. But if I gave you a weird number, let's say that the number was 17 minutes, then you're like, oh crap, that's not an easy fraction. So we gotta go. So we have 17 minutes, and let's do the conversion to hours, or you're gonna take the 17 over 1 times, so you want hours in the top so that the minutes can cancel on the bottom. So in this case, you're going to take 17 minutes cancel out. So you're going to have 17 divided by 60 hours is going to be the fraction, the answer. And so you'll get something that's a little bit over 0.25, and you can calculate and find out what it is. You could do it in many directions. You could say something like, well, and this is the last one, I promise, and we'll leave. So let's say we want to do 1.5 hours, and we want to convert to seconds. How do we do that? Well, start with 1.5 hour over 1. Most people don't know how many seconds are in an hour, but we know how many minutes are in an hour, right? How many is that? Say, come on, bro. I'm a college student. Don't ask me that.
60.
So where do we put it? Up at the top, right? 60 minutes, 1 hour. So the hour is going to cancel. But whatever answer we get here, we're still going to get it in minutes. So since we want to go to seconds, we do this one more time. So we're going to have 60 seconds over 1 minute. So now the minutes cancel out. So now you're going to have an answer that's going to be 1.5 times 60. If I can, yeah, my this thing got a life of its own. But hopefully you get the points. 1.5 times, what the hell? Anyway, my cursor decided to give up. I guess that's time to end. So basically 1.5 times 60 gives you the answer in seconds. I'll stop there because this thing's upset with me. So any questions? All right. Say it again? Not today. So yeah, not today, but even next week. If we get the reef stuff out running smoothly, I will, but don't worry about it for now. Yeah, and my goal is to have this posted by the end of the day as well for anybody that can get it or maybe wants to look at it again. So we'll see the whole class next Monday and you guys in person next Wednesday. So, I think so. If this works smoothly, we'll keep it. I think it will though. So yes. All right. So if there's no more questions. Thank you, everybody.
Thank you so much. Have a nice day.